What if a comet entered our solar system and broke every rule we thought we knew? Imagine an object that defies the fundamental laws of physics, sporting a feature that looks less like nature and more like engineering. This isn't science fiction. It's a thought experiment grounded in a torrent of strange data from real interstellar visitors. We're about to explore a hypothetical scenario based on real science that pushes the boundaries of understanding. Let's delve into it together. The Chilean frame. It all starts with a single unexpected image. Imagine an amateur astronomer, much like the legendary Gennady Borisov, who discovered the first confirmed interstellar comet from his backyard Margo Observatory, peering at the sky from the clear darkness of Chile's Atacama Desert. The date is October 20th, 2025. Her equipment, a 150mm refractor, is pointed at the coordinates for a newly tracked interstellar object, 3I Atlas. What comes back from her cooled CMOS camera after a 60-second exposure isn't a textbook comet. The raw data, captured under pristine verifiable conditions with atmospheric seeing logged at an exceptional 0.7 arcseconds, shows something impossible. This isn't a blurry social media rumor, it's a hard data point from a credible observer. The coordinates match NASA's official Jet Propulsion Laboratory tracking. The equipment metadata is clean, and the image is perfectly sharp. And there, aimed directly at the sun, is a perfectly straight, highly collimated jet of material. This single frame from a small converted farm building becomes the most important astronomical image of the decade, kicking off a firestorm of debate and challenging the very foundation of cometary science. Comet Physics 101. So, why is a sunward pointing jet such a big deal? First, let's cover the basics. Comets are often called cosmic snowballs, a term coined by the brilliant astronomer Fred Whipple back in 1950. His model describes a nucleus made of ice, dust, and rock. As a comet approaches the sun, solar radiation heats its surface, causing ices like water to turn directly into gas, a process called sublimation, at temperatures above -100 degrees Fahrenheit. This process creates a glowing atmosphere around the nucleus called a coma. The sun's influence doesn't stop there. It produces two distinct forces: radiation pressure from photons and the solar wind, a stream of charged particles traveling at over 400 kilometers per second. As explained by solar physicist Eugene Parker, these forces push the gas and dust away, forming two tails. The dust tail is broad and curved. The ion tail, made of charged gas, is thinner and points directly away from the sun, like a windsock in a gale. No matter where the comet is in its orbit, the rule is unwavering. The tails always point away from the sun. This is fundamental observable physics, seen in every comet we've ever studied. The sunward jet. Now, let's go back to that Chilean frame. It throws the rulebook out the window. Instead of a fuzzy coma and majestic tails pointing away from the solar glare, the image of 3I Atlas shows something entirely different. The nucleus is a sharp, dark point. The surrounding coma is strangely faint, with a measured magnitude of only 18.5, far dimmer than expected. But the most shocking feature is a narrow, focused column of material, no more than 2 arcseconds wide, extending from the nucleus directly toward the sun. It's not a tail, it's a jet. Seasoned comet observers, like the renowned planetary scientist David Jewett, would find this image deeply unsettling. The expected anti-solar tail is completely missing, replaced by a feature that seems to violate the basic principles of solar-driven outgassing. The object is actively resisting a 400 km/s solar wind. The image confronts us with a stark contradiction. An object that should be fleeing the sun's power appears to be pointing something straight at it. This single observation demands an explanation, and the easy answers simply don't hold up. Breaking the rules. Let's be clear about how profoundly this hypothetical image breaks the standard cometary model. The physics of solar sublimation dictates that as a comet gets closer to the sun, it should become more active, the coma should brighten, and the tails should grow longer. Under the excellent viewing conditions logged in Chile, a normal comet at this distance would be expected to brighten by at least a full magnitude, displaying a luminous coma and a clearly visible tail. Yet, 3I Atlas shows a minimal coma, and its only significant feature is a jet running in the completely wrong direction. Scientists like Imre Toth, who specialize in comet activity, would immediately suspect an equipment malfunction. Could it be an artifact, like a sensor streak? The data suggests no. The feature is too sharp, too perfectly aligned with the sun's position, and it persists across multiple, independent processing attempts of the raw data. It's too regular to be random noise. We are left with a data point that suggests the rules of sublimation and solar pressure are, for some reason, not applying to this object, a conclusion no scientist would reach lightly. The gauntlet. Every extraordinary claim in astronomy must survive a gauntlet of mundane explanations. The first suspect is always geometry. Sometimes, from Earth's specific vantage point, dust left in a comet's orbit can create an anti-tail. However, anti-tails, studied extensively by scientists like Michael S. P. Kelly during NASA's EPOXY mission, only appear when Earth crosses the comet's orbital plane. On October 20th, Earth was still over 4 degrees away from the orbital plane of 3M Atlas, making a prominent anti-tail highly improbable. More importantly, anti-tails are always broad, diffuse sheets of dust, not the tightly focused jets seen in the image. The next suspect is a transient event, like a pocket of volatile ice erupting. But these outbursts are chaotic and short-lived, rarely lasting more than a few rotations of the nucleus. The sun-facing feature in the Atlas data is persistent across more than 4 hours of observation, making a fleeting eruption unlikely. Finally, atmospheric distortion is ruled out by the observatory's logs. The stars in the image are sharp, proving the sky was stable. After running the checklist, every conventional explanation falls short of explaining the hard data. Chemical anomalies. The weirdness isn't just visual. Spectroscopic analysis of 3I Atlas reveals a chemical composition that is bizarre, even for an interstellar traveler. The data shows a carbon dioxide to water ratio of nearly 8:1, one of the highest ever recorded. For comparison, the famously CO2-rich Comet C 2016 R2 Pan-STARRS had a ratio of about 5:1. This tells us 3I Atlas was formed in a place far different from our own solar system's water-rich environment. But the real smoking gun is the metal content. Preliminary spectra from observatories like the Keck telescope hint at the presence of nickel emission lines, but with a strange absence of iron. In all typical cometary material, iron is at least 10 times more abundant than nickel. The data from 3I Atlas suggests a nickel-rich, iron-poor outflow, a pattern with no known natural precedent. Scientists like Denis Bodowitz, who studied the chemistry of 2I Borisov, would be stunned by these readings. The unique chemistry suggests a nucleus with properties we've never encountered, deepening the mystery of the sunward jet. Retrograde path. The object's path through our solar system is another major red flag. 3I Atlas is on a retrograde orbit, with an inclination of 110 degrees, meaning it's traveling against the flow of planetary traffic. Its immense speed, with a hyperbolic excess velocity measured at 32 kilometers per second, absolutely confirms its interstellar origin. It's a tourist here, not a resident, but its trajectory, combined with its estimated mass, raises fascinating questions. When scientists like Avi Loeb analyzed the first interstellar object, Oumuamua, its slight deviation in trajectory led to the hypothesis that it could be an artificial object, a solar sail. Now, with 3I Atlas, we have a different anomaly. It's not a subtle acceleration, it's a visible, persistent structure that seems to defy solar forces. This sun-facing jet, in the context of its exotic composition and retrograde path, forces us to consider possibilities that stretch natural explanations to their breaking point. Could this jet be a functional feature, perhaps, as propulsion expert Mason Peck has theorized in other contexts, an engineered structure for orbital maneuvering? Perihelion blindness. Here's where the timing gets critical. The comet is scheduled to reach perihelion, its closest approach to the Sun, at a distance of 0.4 astronomical units, on October 29th. At that exact moment it will be hidden from our view, positioned directly behind the Sun in a solar conjunction. This creates a week-long observational blackout for all ground-based telescopes on Earth. Any sudden change in behavior, a fragmentation, a course correction, or a massive energy release, could happen completely undetected. During this period, our only eyes on the comet belong to a handful of space-based instruments. The SOHO Observatory's coronagraph can spot large-scale outbursts, while the Parker Solar Probe might record changes in brightness, but the data will be patchy and delayed. As Noray Rawafi, the project scientist for Parker Solar Probe, knows well, these instruments are designed to study the Sun, not hunt for cometary anomalies. This period of perihelion blindness is the perfect time for something extraordinary to happen, unseen by human eyes.
Space Watchers.
Once 3i Atlas emerges from behind the sun in early November, an army of telescopes will be waiting. The scientific community will be on high alert, and the checklist of what to look for is clear. First is photometry. A sudden jump in brightness could signal a natural outburst, while a steady fade without a growing tail would be highly unusual. Next is morphology. Does the comet finally grow a classic anti-solar tail? Or does the bizarre sunward jet persist? Programs like Pan-STARRS, directed by astronomers such as Ken Chambers, are designed for this kind of monitoring and can detect objects down to a magnitude of 24. They will search for any fragmentation, the appearance of smaller companion objects breaking off the main nucleus. Even tiny, almost imperceptible shifts in its trajectory, measured with a precision of milli-arcseconds, will be meticulously tracked by professional networks. Every new piece of data will be scrutinized, compared, and debated by experts like Comet dynamicist David Nesvorny. The weeks following the solar conjunction will be a critical test for all existing theories.
Emergence.
As the first post-perihelion images arrive, the scientific process will kick into high gear. Interpreting the new data will demand extreme caution. Image processing techniques, how you stack frames or subtract background light, can easily create or hide faint features. A jet that is visible in one astronomer's processed image might vanish in another's. The key, as always, will be reproducibility and peer review. As emphasized by researchers like Michelle Bannister, a claim is only as good as the independent evidence that supports it. No single image will be enough. The global astronomy community will need to achieve a high signal-to-noise ratio, ideally greater than 5, across multiple independent datasets to confirm any anomalous feature. Only a structure that appears consistently can be considered real. The story of 3i Atlas will ultimately be written not by a single dramatic snapshot, but by the slow, careful, and rigorous work of scientists checking, rechecking, and challenging each other's findings. The truth will be found in the consensus of global data. So, we are left standing at a precipice. A hypothetical object, 3i Atlas, backed by puzzling data from real interstellar visitors, forces us to confront the limits of our knowledge. Is its sunward jet a fleeting natural phenomenon, a sign of exotic chemistry we've never seen before? Or is it something that fundamentally bends the rules of physics, hinting at a purpose beyond natural formation? The period of perihelion blindness leaves us in suspense, but the weeks that follow promise a flood of new data. The answers are waiting out there, in the cold dark of space. What do you think is happening with this object? Let us know in the comments below, and don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our cosmos. Thanks for watching Sci and Why.